So 2010, Mech 1, AP Physics C. So students are expected to conduct an experiment to do terminal velocities of a stack of papers. Okay, so it looks like we're going to be increasing the mass and then looking at the terminal velocities. Okay, students change the number of filters, keeping the same shape, so that means that the coefficient's not changing. There's air resistance. Well, yeah, we figured that out. Okay, so then the students expect the force of drag proportional to the square of the speed, where c is a constant. Determine the relationship. Okay, so if I need a relationship, so let's start with, here we go. There is Fg, there is Fr, sum of forces, and the y is equal to may. This is part A. Remember, these types of problems with graphs, first we develop the relationship and then we go from there. So I'm going to say down is positive, so Fg plus Fr. Remember, these things have their own internalized negatives, so we're going to leave that like that. So mg minus, and they say it's of the form cv squared equals may. And now what we're looking for is terminal velocity. So remember, how do we find terminal velocity? We take the limit as v approaches v ter, which is the same thing as a approaches 0. So mg minus cv ter squared is equal to 0, or v ter is equal to the square root of mg over c. There we go. So there's my expression. So now I need to find out what c is. So I think that that's what it is. Yeah. The students, here, there's my data. Assuming functional relationship, use the grid to plot a linear graph to verify m, to verify the relationship. And I'm going to guess here it's going to be, yeah. We look later, it says to use your graph to calculate c. So keeping that in mind, I have m's. Okay, well, that's pretty easy. I have v ter is equal to, remember, we're thinking about putting in the form of y equals mx plus b, the square root of m over c, and then that's times the square, or g over c, excuse me, and that's the square root of m. And so what I can do then is I can take all my masses and just take the square root of them. That's annoying. Actually, why don't we just square both sides? So v ter squared is equal to gc over m. Awesome. So my vertical axis can be v ter squared, and my horizontal axis can be m, and then my slope is just going to be g over c. So that's a nice simple thing to do. So I'm just going to square all my terminal velocities, because that's easier than taking the square root of these really annoying numbers. Okay, and so this is going to be terminal speed squared, vt squared in units of meters squared over seconds squared. Okay, so this is 0.2662, 0.38. I'm keeping to the same number of significant figures as that is. They don't care about it, but like, there's no point in going any further. Okay, 0.85, 1.06 squared. Okay, 1.12. Okay, and that's what I'm doing here. So this is going to be v ter squared in units of meters squared seconds squared. Looking at this, I'm going from about 0.25 to about there. So 1, 2, 3, 4, 5. Okay, I could just go by 0.25. It's 0.25, 0.5, 0.75. Well, actually, hold on. I can go up by 0.2s even. That's nicer. 0.2, 0.4, 0.6, 0.8, 1, and 1.2. I want to use as much of the graph as possible. It's going to make my life easier. This is just obnoxious, but here we go. This is 1, 2, 3, 4, 5, 6, and I'm just going to say times 10 to the negative third for each of them, rather than writing those nasty numbers. So here we go, a little bit bigger than this, but smaller than that, and up to 6, about a 2, up to a little bit below there, and next a little bit below 3, up to 6, 7, so less than halfway. That next 4 points, so right up here, 8, 5. Okay. next 5.10, so there, and then that goes up to 1.12. Boom, that looks like my outlier there. They always have one outlier point, and I'm going to have my best fit line. Perfect. And so that's what my graph looks like. So next, let's see what they want me to do. Oh, shockingly, use your graph to calculate C. Okay, so once again, I'm going to say the slope is equal to, right, we had this on the y, that on the x. The slope is equal to g over c. So slope is equal to 9.81 meters per second squared divided by c. And my slope is equal to, I'm going to come to my graph. I'm going to pick two nice points that are actually on the line there. So boom, I pick that one. It's really nice. Do I have another one that's pretty nice? Yeah, here, that one's pretty nice. And so I've got 1.05 excuse me, meters per second. And that's at 5 times 10 to the negative third kilograms. And then minus, and then this is at 0.75 meters per second. And at a point of, what is that, 3.6 times 10 to the negative third kilograms. Boom. So let's find out what the slope is equal to, and then we'll use that to find C. So 1.05 minus 0.75 is 0.3. I always like doing a little bit of extra work for these. Negative third. I don't need units there because I've shown my units on my plugin. And so then my slope, which I actually don't even need to find the slope itself, but habits. The slope is 214.3. Great. So that means C is equal to, actually, let's look at the units here because that's super interesting. The units here are meters per kilogram seconds, which is kind of awkward, but there it is. So that means that my C is going to equal, so 9.8 meters per second squared over C is equal to meters per kilogram seconds. Let's just like get rid of some of this stuff. Boom. Okay. Apparently the units of this thing are kilogram divided by second. And it's going to be 9.8 divided by that number that we just found. So 0.046 kilograms. Oh, actually, hold on a second. This is meters squared over seconds squared. I messed that up. So this is going to pick up a meter over second. That's what that is equal to. Beautiful. Woof. Okay. So now what else do they want us to do? A particular stack of filters math m is dropped from rest and reaches a speed close to the terminal speed by the time it's fallen vertical distance y. Sketch an approximate graph of speed versus time. Oh, they're just seeing if you know what this graph looks like. So hopefully we know from our study that when you solve this equation that the velocity has that relationship, so it is asymptotic, right, to whatever vector is. So here's the terminal velocity, vt, and there it is. And so they say as close to the terminal speed as fallen y, so that's probably somewhere right around here. We know that it's just about at that terminal velocity. Okay. Suppose you had a graph like the one sketched in CI that had a numerical scale in each axis. Describe how you could use the graph to approximate the distance y. Okay, well, what about a velocity versus time graph? Is distance? The answer to CII is the to approximate the area under the curve, because displacement is equal to the area under a v versus t graph. Okay. D, determine an expression for the appropriate approximate amount of mechanical energy dissipated, delta E, due to the air resistance during this time. Express your terms in terms of y. Okay, so work non-conservative is equal to the change in total energy. So I'm going from an initial total energy, which is mgy, and then finally, we want to know, so final minus initial. Finally, I have kinetic energy, so 1/2 mv tur squared, and initially I had mgy of energy. Okay, and there we go. That is problem 1 off of AP 2010.